Hi, welcome back to the Alkene Edition playlist in organic chemistry. I'm Kevin Tokoph. Please like this video and subscribe to the channel for future videos. That'd be much appreciated. This is actually part 2 of a 2-video series that we're doing on anti-dihydroxylation, which is a pretty useful reaction that we have in organic when we're dealing with alkenes. Okay, and anti-dihydroxylation occurs in 2 successive steps. The reason I chose to break this one into 2 videos for the 2 steps is that the first one, where we use this reagent, MCPBA, a peroxy acid, to form the epoxide, is because by itself, that in and of itself is a very useful reaction where you don't actually have to do this second step, which is going to be with hydronium. Because there may be cases where you want to form an epoxide, but maybe the other functional group you want actually is not a diol with 2 hydroxyl groups. So sometimes you may wish to just cut it off at the epoxide and do something else. So I wanted to do epoxidation in the first video. So that brings up the first point. The first video was on epoxide formation or epoxidation. And if you remember what an epoxide was, it was just a 3-membered ring like this. There could be other groups sticking off, but 2 of the atoms are carbon and then the other one is oxygen. And as a result of the ring and angle strain, the epoxide is actually very reactive and you can get it to do all sorts of things. Okay, and that was done with MCPBA. The second step, at least from the perspective of alkene additions, is we're going to want to use hydronium, and it's going to give us a compound with 2 hydroxyl groups that are 1,2 to one another. Okay, so they're on adjacent carbons. Now, in the name, as it suggests, it is an anti-addition overall. So when you go from the alkene ultimately through the second step to the diol, and that's what this is a diol because it has 2 alcohol groups. The alcohol group should be on opposite sides of where the double bond was. So the 2 carbons that were in the double bond were these 2 carbons that I've labeled in green. And notice that the left hydroxyl group is on a wedge, the right one is on a dash. So they are anti to one another. Okay. Now remember that when we did the MCPBA epoxidation reaction, I can get the opposite stereochemistry for the epoxide. Notice again here that the epoxide is on wedges, but I can actually get the epoxide to be on dashes, in which case when I use hydronium, I'm going to get the opposite product. So notice in this case that this alcohol, the left one is on a dash, opposite this one, and this one is also on a wedge. So depending on the presence of other chirality centers, when you do this reaction, you're either going to get 2 enantiomers, or you can actually get diastereomers as well. So you do have to watch out for that. Okay, so you get enantiomers. All right? Or in general, stereoisomers. Now what I want to do at this point is I want to take a look at the mechanism, because that's actually pretty important. Now, there is one thing I want to point out about this mechanism, okay? This right here that I'm about to do is a very, very general mechanism, okay? Remember, these 2 carbons that are actually part of the epoxide right there, you could have other R groups off of each one. You could have hydrogens or a mixture of the 2. And so the mechanism that we're going to look at actually can change a little bit depending on how many substituents each of those carbons has. So in some cases, the nucleophile, which in this case is actually going to be the water, can attack the more substituted carbon, but in some cases it attacks the less substituted. We're not considering any of that here because for the purpose of addition reactions and predicting the products, you don't actually need to understand that. But when we go much later into OChem 2 topics and we start doing more epoxide reactions, we'll actually look at the implications there, but you don't need that here. So just understand this is a very general mechanism, but this is what happens. So remember, the epoxide oxygen here has lone pairs on it. And when we throw this in with the hydronium, which is ultimately the second step of overall anti-dihydroxylation, the epoxide will actually deprotonate the hydronium, and so you get a protonated epoxide. Now, epoxides by themselves are extremely reactive. However, protonated epoxides are significantly more reactive than just regular epoxides. So what ends up happening is both of these carbons, to some extent, become very electrophilic. So they're going to have partial positives on them. And depending on the substituents, one can be greater than the other. But in any case, water here is the nucleophile, and it's going to attack one of these carbons and free this oxygen on the other side of the other carbon. Ultimately, that's going to give you one alcohol right here, and then on the other carbon, there is a protonated oxygen here. Then in one more step, there's another water molecule right here that's going to do the final proton transfer to neutralize this functional group and make the alcohol. The water here is actually going to deprotonate this oxygen, and that's going to ultimately give you a very important functional group, and that is a diol. Okay, and ultimately, because it's an anti-addition, we give this a pretty special name. It's not just a diol, it is a trans-diol. Now, I haven't indicated stereochemistry here, but in any case, if one of these was on a wedge, the other one would be on a dash, and so forth, just like we had shown over here when we were first introducing this. Okay, so once again, with this, the best way to get good at it is to start predicting the products. All right, so the best way to get good at this is just to do practice problems. So right here, we're going to practice. All right, so what we're going to do in this is we're not just going to epoxidate. I also want to do the second step of using hydronium to perform the full anti-dihydroxylation. So again, I always say this in each of these videos where we do this, but one of the techniques I use, I frequently use to teach, how you figure out where different functional groups go. Basically for that, there's a video earlier on in this playlist that explains it in a lot of detail. Here, I'm just going to go ahead and do it and explain it, and hopefully you can catch on, or if you need more explanation, go watch that video. But the technique starts with looking for the alkene, the double bond, and just simply drawing a dotted line right through it, okay? Now, what you do is you just, and it's arbitrary which side you pick, but I can either pick the above the dotted line or below it to remain the same. Okay, I'm going to pick the bottom side, and essentially what I mean by remain the same is sort of remain in the plane of the screen. Okay, right now the alkene itself it's planar, so everything right now is for the most part in the plane of the screen. But when I say in the plane of the screen, it means that it's on just a normal solid line. It's not on a wedge or a dash. So below that, I'm just going to keep everything exactly the same, just like that. Then what I'm going to do is I'm going to put in the hydroxyl groups. Well, one of them is obviously going to go here, and I'm going to just put that on a wedge. But then since it's an anti-addition, the other one then has to go right here. And so it's on a dash. They're anti. Now I'm going to go back in and fill in everything else. It might help to remember there's also a hydrogen there. Well, since this OH is on a wedge, that hydrogen right there then has to go on a dash. Likewise, this methyl group right there, okay, the methyl group, here this OH is on a dash, so the methyl has to go on a wedge. And that's one of the products, but like we said before in the previous explanation, we can get another one, usually in an enantiomer, but it could be a diastereomer as well. Okay, so in this case, I've drawn everything below that dotted red line the same. Now I'm going to go back in and put this OH on a dash, and then put this one on a wedge, just like that, so that they're anti to each other, right? Then I'll just go back in and fill everything else in. The hydrogen in the circle, now that has to go on a wedge, right? Because I'm just flipping the stereochemistry of everything, right? And then this methyl group now is therefore on a dash, okay? And those are my two products. Now, ultimately, because this position right there has 4 different groups, these two are enantiomeric to one another. This position over here on the right, that's not a chiral center because it has 2 methyl groups, okay? Let's work on the next one. All right, so this is cyclopentene. We've seen this molecule before. Here's the alkene. I'm going to work my technique. I'm going to put the dotted line right through that double bond. In this case, it would probably be easier just to keep everything on top here in the plane the same. Sometimes you just pick what's easiest and you just go with that. So everything above that's going to remain the same. So I'm going to just, oops, not supposed to be red. That's supposed to be white. So I'm going to go ahead and, let's see, there we go. Just draw that, right? And then I have to put the 2 hydroxyl groups. It doesn't matter where I put them. I'm going to put this one going this way on the wedge. And then I'm going to put the other one on the other carbon. That has to go on a dash because it's an anti-addition, right? Hopefully that makes sense. And just recall that there are 2 hydrogens, 1 on each of these carbons. And so if you wanted to, you could go ahead and just put this hydrogen on the dash, and then this hydrogen would obviously be on a wedge. Okay? But like we said, you can get something else. Typically, it's a good idea to just practice drawing it. So I have this. I kept everything above the dotted line the same. Now I'm going to put the hydroxyl groups in. But again, this one on the left, therefore, has to be on a dash because I'm flipping everything. And this one would have to be on a wedge. Okay? And then I can go ahead and put in the hydrogens too. This one over here this hydrogen would have to be on a wedge, and then this one, of course, would have to be on a dash. Okay? Now, you look at these 2 things and you say, okay, this carbon right here has 4 different groups, it's chiral. This has 4 different groups, it's chiral. And you can test this to see if it truly is in an enantiomer. You might think, well, maybe I can put an axis, down through this, and kind of messed that up, and then flip it over 180 degrees. When you do that, this hydroxyl group would be on a wedge over here. When you do the 180 degree flip, that hydroxyl group would be on a dash over here, and it certainly is not the same compound as over here. So these are enantiomers to one another. Okay, so hopefully that makes sense. All right. This is benzene, right? We hopefully by now can recognize benzene, and we can also at least maybe not fully understand aromaticity, but we can understand that it is aromatic. And one of the things is when you have these addition reactions that normally work on, simple alkenes, they don't tend to work on aromatic compounds because aromatic compounds like benzene are incredibly stable. So we can use MCPBA and hydronium on this. We could certainly do that. But ultimately, when you do this on benzene, there is no reaction. Okay? Doesn't work on benzene. All right. Suppose we have this compound right here. Suppose that I have this, a diene. So this is it's not a conjugated diene. These are isolated dienes. So one double bond here, one double bond here. Therefore, ene for alkene, and there's 2 of them. So di. And I'm going to put in excess MCPBA and H3O+. The reason I do that is because for every one of these molecules, I would have to have 2 MCPBAs at least. So I'm just going to put excess of these reagents in. Well, what's going to happen? Well, I'm just going to get epoxidation and then the production of the diol. But it's a diol for each of these, so overall it's a tetraol. Okay, kind of a weird thing to say, but what we're going to do is we're going to simply work on this one, this double bond right here, and then we can work on it separately from this one. Okay, so this is a little bit of a challenge problem. All right. So the first thing we're going to do is just draw the carbon skeleton. Now, one of the things to remember is you more or less have to treat this double bond as being separate from this one. You do have to treat them separately, all right? So it may also help just to remember I have 2 hydrogens right there. And for the purpose, and also another one there, for the purpose of the red one, I'm more or less just going to pick, I'm going to pick everything on top of this to be the same, and that's actually what I've done here. Let me go ahead and just put that hydrogen in there. So everything on top is going to be the same. Whenever I do the blue one, I'm also, just for the sake of simplicity, I'm going to pick everything on the top there to be the same. And again, it may also help to remember that I also have hydrogens here, okay? In which case, then I'm going to want to put another hydrogen on there, okay? Now, I'm going to put the OH groups in, okay? Put those OH groups in. So that means that one of them may be on this carbon right here. I would have to put on a wedge, right? But that means that the other one would have to be on a dash, right? Hopefully that makes sense. And then of course I can go in and fill in everything else. So I have a hydrogen going down like that. That one would have to be on a dash. And then this one over here, it's getting a little messy, but that one would obviously have to be on a wedge. Okay. Now I'll go and do this other one. I'll do this one in purple just to get the colors different. Again, probably what I'll do is just for the sake of consistency, I'll go ahead and just put this one as an OH on a wedge on this one, and then this one will go ahead and be on a dash. Okay. Now, remember that you're treating each, oh, and then also, sorry, give me 1 second. I also forgot I have to put in this hydrogen there, and then I need to put in this there on a wedge. Okay, but that's beside the point. Anyways, remember another thing also. I'm treating the left double bond in red different from the right one that's in blue. So what I can do is, what if, for example, I'm going to just give you a hypothetical. What if I had another one where this OH was on a wedge, just like in the previous one, and this one was also on a dash, and then I can just go ahead and I can draw in all the other little hydrogens. They're not really of any consequence, though. So I have that. But what if I kept the purple ones the same, but what if the blue ones were the ones that flipped? So now this OH is on dashes, and then this OH is on a wedge, which means that here I have hydrogen on a dash, hydrogen on a wedge. Well, that's a perfectly possible product because it's very possible that maybe when I formed the epoxide for the first one, compound 1, the epoxide here was, had some stereochemistry and the second one had another stereochemistry. But then when I get the second product, number 2, maybe the first epoxide had the opposite chemistry, but the second epoxide was the same as the first. So that means on the second one, there wouldn't be any change that you would see. But now what happens, suppose I have this. So you can probably see where this is going at this point, hopefully. Okay, what if now, and actually I kind of messed that up. Give me 1 second. Messed up that. What if, did not mean to do that. Sorry about that. Anyways, what if I now had this? Okay, what if instead now the blue one down here were the same orientation? So maybe I had the OH on the wedge there. I had an OH on the dash there. Okay. And then that, of course, means that this hydrogen would be on the dash, and this one would be on the wedge, right? But suppose now it's the purple one that changes. Well, then I'm just going to put the OH here on the dash, and then I'm going to put this OH here on the wedge. Hopefully that makes a little bit of sense. I'm sort of just making different combinations of each. And then this hydrogen would be on the dash, and then this one is on a wedge, okay? So that probably begs the question, there's probably one more combination I can make. Let's figure out what that is. Okay, so now I have 2 here, 1 and 3, that have the first OH on a wedge. This one has it on a dash, so that's probably what I want to do, put that OH on a dash, which means that this one has to be on a wedge because they're anti, right? And then let me just very quickly go in and fill in this hydrogen right there. And then a hydrogen right here, right? But now for the purple one, why don't we go ahead and let's, I don't know, flip this one, right? Flip this as well. So maybe now, okay, I have this on a dash like that. Sometimes it doesn't write well. And then I have this one on a wedge, okay? So this purple one is similar to over here, but the blue one's flipped. Okay, and then I can go ahead and fill in. I can fill in this hydrogen on a wedge, and then of course that one's on a dash. Okay, and that would be product 4. So here the key is when you do anti-dihydroxylation on something that is a diene, and especially when they're isolated double bonds and not conjugated, you have the capacity to actually get 4 products. When you are doing, when you're trying to figure out how many products you should have if you were to get some kind of diene or triene or something, and it goes on, you can do this quick little formula. You can say that the number of products that I should get, theoretically, and some might be easier to form than others, but whatever, the number of products I get is 2 to the power of the number of double bonds. So if I were to have 2 double bonds like I have here, how many products? Well, it's 2 to the 2, which is 2 squared, and that's 4. If I have 3 double bonds, I just put 3 in here on the exponent, and it's 2 to the 3rd, which is 8. So I should have 8. If I had 4 double bonds, I could get 16, and so on and so forth. Okay, so hopefully that makes a little bit of sense, and anti-dihydroxylation is clear to you now. Okay, you're just following this kind of this technique that I showed you in many videos. You draw the dotted line, and you have to know whether it's syn or anti, but you just kind of follow the same rule we've been doing in every video. Now, one thing I do want to show you is that this is one of the reactions that we have in this chapter where there are biological applications. So if you're not interested in that, you don't necessarily have to watch this. They probably wouldn't test over anything like this, to be perfectly honest. But it's just interesting. So a lot of times, not all the time, I mean, there are certainly compounds in biochemistry and biology, natural compounds that have carbon-carbon double bonds. But there's a lot of compounds that are just straight hydrocarbons, and they have a degree of unsaturation. They have a double bond. For instance, this compound right here, this has 4 carbons. This is actually cis butene. This is cis-butene. That's the name of the compound. And it's very possible that you could potentially somehow either ingest it for whatever reason. Maybe you're in a lab dealing with it, just a little sprays off in your mouth, you swallow it and so forth. Or it's possible that you could inhale it or something. Somehow it could get into your body. And because it's not a normal biomolecule, your body doesn't have a normal enzymatic pathway to deal with it. You've probably heard of glycolysis. If you eat sugar, like glucose, glycolysis burns it. It's a pathway made for that. So when you have strange foreign molecules like this, you have a set of enzymes that can deal with it, particularly in the case of alkenes. So an example. One of the enzymes we've mentioned in previous videos is cytochrome P450. It's the largest family of enzymes in humans and all mammals. It's a liver enzyme for the most part, although it's also in the nasal mucosa. And one of the reactions we talked about in the last video when we talked about epoxidation was cytochrome P450 epoxidase. And you can see the reaction that it does. There's some other molecules it uses to do this, but in any case, it takes the alkene and it makes the epoxide like we're used to seeing. So this is it's the analog of using MCPBA. Now, remember, in biochemistry, you don't have molecules like that. It's not like this enzyme uses MCPBA. It uses a different set of reagents, but it accomplishes the same thing. So you can sort of think of this as like the identical analog. Now, one thing we can go further, because certainly you don't want this floating around, because if you had DNA that was a nucleophile that attacked one of these, you'd form an adduct. So one thing that the liver also has is an auxiliary enzyme called epoxide hydrolase. And you look at this and you say, well, probably the analog to this in organic would be the second step, H3O+. And in fact, it is. So just like you would take this cis-butene, use MCPBA and H3O+ to perform an anti-dihydroxylation, epoxide hydrolase accomplishes the same net thing. So you start with an epoxide. This enzyme, epoxide hydrolase, in the liver grabs a hold of it, and it forms this compound, which is just a diol. And to be specific, again, it is a trans diol. Okay, now I haven't indicated stereochemistry here, but remember, say for instance, if this was on a wedge, then this one would be a dash, and sometimes the enantiomer also, or diastereomer, is formed as well. Okay, one more example just to kind of illustrate the point, and I brought this up in the previous video, that remember that a lot of the rules you have in organic chemistry as a science itself can be violated in biology by enzymes. So I mentioned that normally when if we were to just throw in some MCPBA and then H3O+ in 2 separate steps, right? If I were to do that to benzene, what happens? No reaction, okay? But for a human or living system, that's not good enough. Say if I was to ingest benzene, benzene is a known carcinogen, a mutagen. It can actually, if a woman's pregnant and she was to get benzene in her, it can actually cause birth defects. So it's one of those compounds as well. So the liver will also get rid of this. And the way it does it is it sort of treats each of these double bonds as if they're completely isolated from the system. This molecule benzene is aromatic, but it treats this double bond as if these other two don't even exist. That's how powerful this enzyme is. So again, it's violating your organic rules, but it's able to do something just identical to what we've seen. So cytochrome P450 epoxidase, liver enzyme, the same one that I talked about in the previous video and up here. So it's able to take this double bond, and what does it do? It does exactly what we saw before. It forms an epoxide. Okay, and then, as we would expect based on this analogy above, epoxide hydrolase, the auxiliary enzyme to this, in the liver, then performs a hydrolysis of the epoxide, and again, you form a trans diol, as shown here. And once again, we could do this if we want. You know, maybe this one is on a wedge and this is on a dash, but you could get the enantiomer as well. But in any case, this is what happens. And the reason the liver does this is because one of the ways the body excretes foreign compounds is it does it based on water solubility, because you're going to excrete it in the urine, right? The urine is aqueous, okay, has other things in it, but it's mainly water. So you'd want it to be soluble in water. Well, let me ask you this. What's more soluble in water, benzene or this diol? Well, the alcohols can hydrogen bond with the water in the urine and the filtrate in the kidneys, and so this compound is significantly more excretable than benzene is. And also, it's a lot less dangerous, okay? It's not as carcinogenic. So hopefully this video gave you a little bit of intuition on anti-dihydroxylation. In the next video, we're going to go over the opposite of this, as you might have guessed, syn dihydroxylation. And we're going to find that the mechanism is completely different, and the reagents are very, very unique and different. So I hope this video helped. Make sure to like the video, subscribe to the channel. Thanks. Hope this helped. Have a good day.